Great. It's my pleasure to introduce Ilias Magoulas. He's currently a postdoc at Emory University in Georgia, and he did his PhD here at MSU, I believe. So we're happy he came back and will be. Oh, great. And it sounds like his advisor is here too. I'm not sure if you can see that on the feed. But we're very excited to have him back. And we are going to hear from him about CNOT-Efficient Circuits for arbitrary rank many-body fermionic and qubit excitations. So without further ado, Ilias, please take it away.
Well, thank you very much for having me. As I said earlier, I would prefer to be there in person, but we can do this some other time. And I could see some familiar faces in the audience, so that is good. So as you can see from the title of my presentation, today I will discuss CNOT-efficient circuits for arbitrary rank many-body fermionic and qubit excitations. Or if we want to bring this down to earth, I will show how to improve the efficiency and robustness of quantum algorithms for computational chemistry. So first of all, why are quantum computers useful for computational chemistry? 40 years ago, Feynman said that nature isn't classical, and if you want to make a simulation of nature, you better make it quantum mechanical. But in fact, Feynman also went one step further, and he said that the rule of simulation that he would like to have is that the number of computer elements that are needed to simulate the physical system, they need to be proportional to the size of that system. So from general chemistry, we know that the wave function of a molecule can be represented as a molecular orbital diagram or Slater determinant shown here. So this turns out to be a pretty good picture when we have molecules at their equilibrium geometry. And in this case, the wave function is dominated by a single Slater determinant. However, things get trickier when we have bond breaking. So in the case of single bond breaking, it can happen that you can have two Slater determinants that have an equally large contribution to your wave function. And then there are extreme situations known as strong correlation, in which case you can have multiple, if not all, Slater determinants having equal and very small weights in your wave function. And what that means is that if you want to have an exact description, there is no way around it. You need to consider all Slater determinants. As an example of a strongly correlated system, we have this cube of 64 hydrogen atoms. So what you want to do is you want to study the symmetric dissociation into 64 individual hydrogen atoms. The total number of Slater determinants is given by this expression. And you see here, K is the number of spatial orbitals, and N alpha and N beta are the numbers of alpha and beta electrons, or spin up and spin down electrons, if you like. So even if we use a minimum basis set, the number of Slater determinants is astronomical. So if you wanted to have an exact description of the system, you would have to diagonalize a 10 to the 36 by 10 to the 36 matrix, which is impossible. And what is even worse is that the scaling of the number of determinants is factorial with a system size. So that's nowhere near what Feynman wanted. However, if we were able to use a perfect quantum computer, we would only need 128 qubits. And 128 is equal to the number of spin orbitals in our system. And this makes Feynman happy. So now some basics of quantum computing. So on a classical device, the fundamental unit of information is a bit, and it can have values of 0 and 1. On our quantum device, the fundamental unit of information is a qubit, and it can exist in this superposition of the 0 and 1 states. So we can envision that the state of a qubit lies on the surface of a unit sphere, which is known as the Bloch sphere. On the classical machine, if you have 2 bits, they can exist in one of these 4 states, while on the quantum realm, if we have 2 qubits, they can exist in this superposition of the 4 base states. What is important to note is that it is not always possible for us to decompose a 2-qubit state into a tensor product of single qubit states. If this is not true, then we have an entangled state. On the classical computer, we have logical gates that can operate on the bits, and we have the single bit NOT gate. So in this case, if the input is 0, the output will be 1, and vice versa. If the input is 1, the output will be 0. On the quantum device, we also have quantum gates that operate on qubits, and we have single qubit gates, such as the X, Y, and Z Pauli matrices, the Hadamard gate, the S gate, and so on. And all single qubit gates are 2x2 unitary matrices. And this is the quantum circuit representing the X gate. So if the input has this form, after we operate with the X gate, we see that the X gate will flip zeros into ones and ones into zeros. So essentially, the X gate is the quantum analog of the NOT gate. On a classical computer, we also have gates that act on 2 bits, and there are many such examples. And here we have the AND gate. So if the inputs are A and B, the output will be A times B. We also have gates acting on 2 qubits on the quantum device, and the most famous example is the control NOT gate, or CNOT. Again, it is important to note that all 2-qubit gates are 4x4 unitary matrices. And this is the circuit representation of the CNOT gate. So in this particular example, the top qubit is the control and the bottom qubit is the target. If the top qubit is in the 0 state, nothing will happen at the bottom qubit. If the top qubit is in the 1 state, then an X gate will be applied at the bottom qubit. So for example, if we have a 2-qubit state that looks like this, we see that in both of these components, Q0 is in the 0 state, but on this one, Q1 is in the 0 state, and here is in the 1 state. After we apply the CNOT gate, nothing happens on the first component because Q1 is 0. But on the second component, we will flip the state of Q0 because Q1 is in the 1 state. On the classical computer, we have circuits that are sequences of logical gates, and we also have algorithms that are circuits designed to solve a particular problem. And of course, we have the corresponding definitions on the quantum device. So what we want to accomplish is we want to use a quantum computer to solve the electronic Schrödinger equation for a given molecular system. And for the purposes of this talk, I will be focusing on ansatz-dependent hybrid quantum classical approaches. So first, we need to decide on a Hamiltonian, which means that we have to pick a molecule that we want to study. Then we need to construct a trial state, which is expressed as a parameterized unitary acting on some reference state. And we need to have an initial guess for our parameters. Once we have this information, we can then pass it on to our quantum computer. And without loss of generality, we can imagine that the quantum computer starts at the 0 state. So the first step is for us to realize the trial state on the quantum device. So first, we apply a unitary operator uref that will rotate the 0 state into our reference state. And then you apply the unitary ut that will rotate phi into your trial state. Once this trial state is realized on the quantum device, we can perform various unitary manipulations to it. And then we will perform some measurements. The outcome of these measurements will be some function of these parameters. And the first question we ask is, are we converged? If we are converged, then we return the converged energy and state. If we are not, then this information will be passed on a classical optimizer that will determine the values of the parameters for the next iteration and feed them back to your quantum computer. And this cycle is repeated until convergence is reached. However, before we're able to plug this information into our quantum device, we have to translate it into a language that the quantum computer can understand. And this is done by what is known as fermionic encoding, which is a mapping that allows one to represent a computational chemistry problem on a quantum computer. I will use the minimum basic description of H2 as an example. And in this case, we have just 2 spatial orbitals, one sigma g and one sigma u. And this is how our reference Hartree-Fock state will look like. In second quantization, this is how your Hamiltonian looks like. So we have 1 body and 2 body terms. By taking advantage of the various symmetries of this problem, we can derive the following relationship between the 1 and 2 electron integrals. And this allows us to write the Hamiltonian for H2 in second quantization. Having this information, we can then use the Jordan-Wigner mapping to translate it onto the corresponding expression for your quantum computer. And for the purposes of this talk, I will be exclusively using the Jordan-Wigner mapping. So we see that in our quantum device, the Hamiltonian is comprised only of the X, Y, and Z gates and nothing more. And this is how the Jordan-Wigner mapping is defined. So this is the annihilation and creation operators in second quantization, and this is how they are mapped onto your quantum computer. So here, QP and QP dagger are the corresponding annihilation and creation operators for a qubit. And we can write them explicitly in terms of X and Y gates like this. The strings of Z operators at the end bring back the information about the fermionic sign. So knowing these relations, we can translate any second quantized operator into a corresponding expression for our quantum computer. We have already seen how the Hamiltonian can be translated. So what I will be focusing next is the ansatz. And I will be using chemically inspired ansatz derived from coupled cluster theory. So in coupled cluster theory, we use the exponential wave function ansatz, where we have e to the t acting on our single reference determinant. And T is the cluster operator, and it is expressed in terms of its many body components here. So when T1 acts on P, it excites one electron in all possible ways. T2 excites two electrons in all possible ways. T3, three electrons in all possible ways, and so on. Depending on the level of truncation in the cluster operator, we can arrive at a hierarchy of coupled cluster approaches. We have, for example, coupled cluster with singles and doubles, singles, doubles, triples, singles, doubles, triples, quadruples, and so on. And if the level of truncation is equal to n, where n is the number of electrons of our system, then we have an exact full configuration interaction description. So focusing on this exact description, if we plug in the exponential wave function ansatz into the Schrödinger equation and then multiply from the left by e to the minus t, we obtain what is known as the connected cluster form of the Schrödinger equation, where h bar is a similarity transform Hamiltonian, and it is defined here. By projecting the connected cluster form of the Schrödinger equation onto the manifold of excited slither determinants, we obtain the coupled cluster equations that we can solve them for the cluster amplitudes, which are the little t guys shown here. Once we solve the system of equations, we can obtain the coupled cluster energy by simply projecting on the reference determinant. So why would we like to use ansatz based on coupled cluster theory? Well, there are various reasons why. So first of all, coupled cluster leads to size-extensive approximations, which means that there is no loss of accuracy when the system is made larger. Furthermore, it leads to size-consistent approximations as long as the reference is separable. And this allows us to study fragmentation phenomena such as bond breaking, which are of paramount importance in chemistry. And finally, it is characterized by a fast convergence towards the exact full configuration interaction solution, and this is true even in moderately correlated situations. There is one problem. The thing is that quantum gates are unitary operators, and the conventional coupled cluster wave function ansatz e to the t is not unitary. Nevertheless, there exists a unitary extension of coupled cluster where we utilize a slightly different ansatz. So now our ansatz look like this. We have e to the t minus t dagger. So t is an excitation operator and t dagger is a de-excitation operator. The presence of de-excitation operators means that the UCC approach is intractable on a classical computer. Nevertheless, the UCC ansatz can efficiently be implemented on a quantum computer as long as we use a finite order Trotter-Suzuki decomposition. And in this particular example, we use a first order decomposition. So instead of working with this exponential, we approximate it as a product of these exponentials. And these kappa mu operators are defined in this way. These are the anti-Hermitian excitation operators. So for the rest of the talk, I will be focusing on these exponentials and how we can efficiently implement them on our quantum device. And I will start with a simple example of a single fermionic excitation, and this will be the standard approach. So this is how your unitary looks like. We can then use the Jordan-Wigner transformation to translate the individual components into their corresponding X and Y gates. And this is how your exponential will look like on the quantum device. And for the last step, we will use the fact that if you have Pauli strings that originate from the same second quantized operator, then they commute, which allows us to represent this exponential as a product of exponentials exactly. So now that we know how we can translate this into this, the next thing to look at is the corresponding quantum circuit. And this is how the quantum circuit will look like. So on the left, we have the quantum circuit representing the first exponential, and on the right, the quantum circuit representing this exponential. We see that the quantum circuit contains single qubit gates, which are these boxes shown here, and 2 qubit gates, which are the CNOTs. The important thing to note is that we need 4 CNOT staircases to implement a single fermionic excitation. We can do the same analysis for a double fermionic excitation. And in this case, on the quantum device, you end up with these 8 exponentials. And this is the quantum circuit implementing the first 2, the next 2, the next 2, and the last 2. And again, the important thing to pay attention to is that now we need 16 CNOT staircases. And in fact, we can generalize this to the case of an n-tuple fermionic excitation. And in a compact form, the circuit will look like this. So you will have 2 to the 2n minus 1 copies of this circuit and 2 to the 2n minus 1 copies of that circuit. And in total, you will need 2 to the 2n CNOT staircases for an n-tuple fermionic excitation. So you might be wondering, why do I focus so much on these CNOT staircases? Well, as it turns out, not all is great with physical realization of quantum computers. In fact, the quantum devices that we currently have are plagued by various sources of errors. We have imperfections of physical qubits, limited connectivity among qubits, decoherence of quantum states, measurement errors, and errors in experimental quantum gates. And this last part is what I will focus on. So as it turns out, CNOT gates dominate the gate errors. In fact, a single CNOT gate has approximately 10 times the error than a single qubit gate. And we have seen that these circuits have lots of CNOTs. So it is crucial for us, if we want to get meaningful results out of our quantum devices, to reduce the number of CNOTs as much as possible without, however, sacrificing accuracy. And this was the problem that Francesco and I tried to tackle in our first paper. So what you will see here is the number of CNOTs in a logarithmic scale required to implement various kinds of excitations. We have triples, quadruples, pentuples, and hextuples. And in blue, you will see the number of CNOTs required using the standard approach. And in red, you will see the number of CNOTs required using the novel circuits that we proposed. So for a triple excitation with a standard approach, you need 320 CNOTs. But using our novel circuits, you need only 42. So this is an amazing reduction of 87%. What is even more impressive is that the percent reduction gets better and better as you go to higher rank excitations. So if we look at hextuple excitations, the standard approach needed more than 45,000 CNOTs, but with our scheme, you need about 2,000. One thing I forgot to mention is that the novel circuits that we propose are actually equivalent to the standard ones. And what that means is that there is no loss of accuracy by switching from the standard circuits to what we proposed. Now the question is, how were we able to do this? So the simplest way to reduce the number of CNOTs is to replace fermionic excitations by qubit ones. And what that means is that if you go back and see how we use the Jordan-Wigner transformation to translate between second quantization and our quantum computer, you simply neglect these strings of Z operators at the end. Now, these are the relations that the qubit creation and annihilation operators obey. And as it turns out, they are not exactly bosonic, not exactly fermionic. Some people in the literature call them parafermionic. What is important for our purposes is that by removing these strings of Z operators, the qubit excitations are local. And what that means is that they only operate on the qubits that are involved in the excitation process. And this is why you can reduce the number of CNOTs. So for example, this is how your exponential would look like for an n-tuple qubit excitation. And this is the circuit. So in principle, we still have 2 to the 2n CNOT staircases. The thing is that now the CNOTs contained in each of these staircases are much fewer. And in fact, for a CNOT excitation, we can have an analytic count of the number of CNOTs. Now, as it turns out, this is not the most compact way for you to perform a qubit excitation. For us to see how to derive the most compact way, we will have to look how this exponential operates on a generic basis state. So first we start with simple single qubit excitations. So we have this exponential operator acting on this generic basis state. So in general, the outcome of this operation will give you back the same basis state unless one of these two conditions is satisfied. So if the first condition is satisfied, we have the single qubit excitation acting on the ground state. And we can use a Taylor expansion, and we will find that the outcome of this operation is a cosine theta times the ground state plus a sine theta times the excited state. We can repeat the same procedure when we're acting on the excited state. And we will see that in this case, we have a minus sine theta times the ground state plus cosine theta times the excited state. Now, depending on how familiar you are with quantum computing or quantum gates, this structure here resembles the operation of an RY gate. And what that implies is that we should be possible to represent these qubit excitations, the single qubit excitation, by using some form of an RY gate. And indeed, this is the circuit that will implement a single qubit excitation. It is possible for us to see how this circuit performs on each one of the individual basis states to prove that indeed it performs a single qubit excitation, but I'm not gonna drag you through it. And we can perform the same analysis for a double qubit excitation. So in this case, we have this unitary acting on this generic basis state. Again, we will end up with the same state unless one of these two conditions is satisfied. And we see that we have a similar structure. And indeed, the circuit can be expressed in terms of an RY gate. This time, the RY gate is multiply controlled. So the RY gate will be applied only if this qubit is in the 0 state, this qubit is in the 1 state, and this qubit is in the 0 state. So we see that we have control and anti-control qubits. These circuits were already proposed in 2020 by Yordanov and co-workers. So what Francesco and I did was to extend their approach to n-tuple fermionic excitations and qubit excitations. So this is how the circuit would look like in the case of an n-tuple qubit excitation. Now the question is, how many CNOTs does this circuit contain?
Hey, Ilias, can you hear me?
Yes.
Can I ask you a quick question? So I was sort of waiting to hear how you're able to just do things in terms of the qubit excitations. I mean, don't you have to keep track of the anti-commutation relations?
Well, this is already encoded in the translation. So essentially, it is an approximation if I go back, although that is something that I will discuss later. So by doing this translation, you're essentially losing the information of the fermionic sign.
I see. And is that going to present itself as a huge loss, or are you still able to do some things?
Well, I think you will have to wait and see.
Sure. Okay.
just to leave some suspense for later.
He did mention that his product circuit is equivalent to the original circuit, which is confusing to me. Let's see.
Yeah, thank you. Sorry, keep going, please.
Okay. So now in terms of number of CNOTs, so for this circuit, we will need 4 times n minus 1 CNOTs for these constructions here shown in blue. We need to add 2 more CNOTs for these guys. And then the question is, how many CNOTs will we need when we decompose this multiply controlled RY gate into single qubit gates and CNOTs? So the approach that Yordanov used, and that's the one that we also adopted, requires an exponential number of CNOTs, which is 2 to the 2n minus 1. So there is still an exponential cost, but this is an exponential cost of CNOTs, not CNOT staircases. And you can see here that also the exponent is smaller than the one we had in terms of CNOT staircases. So this is where the big savings come from. So we saw that by replacing fermionic excitations by qubit ones, we can reduce the number of CNOT gates. There is, however, one problem that by doing this, we potentially sacrifice the proper fermionic sign structure of the desired state. And we can see that by looking at how the second quantized and qubit creation operators behave. So we see that when we have this second quantized creation operator acting on this generic state, we have a 1 minus NP condition times this sign factor. If we go back to the qubit creation operator, we have a similar 1 minus QP condition, but we lose the information about the fermionic sign. And then the question is, how detrimental will that be for our computations? So this is something that we looked into, and we used as an example the symmetric dissociation of the H6 linear chain using a minimum basis set. And this is a prototypical system for strong correlation. So here we have the errors with respect to full CI. And this is how the qubit UCCSD method behaves. By including triples, we have an improvement. And by going to quadruples, there is a major improvement. So the good news is that if you use qubit approaches, they will still converge to the correct full CI limit. The problem is that this convergence will be much slower than when using fermions. So this is how the fermionic UCCSD method behaves. And you can see that it is already better than the nominally higher level qubit UCCSD-T approach. If we use triples in the fermionic case, we're almost as good as quadruples in the qubit case. And if we have quadruples in the case of fermions, UCCSD-TQ is practically exact across the board. So yes, if we use qubits, we can reduce the number of CNOTs, but there is this problem of slow convergence. So what we wanted to do is, can we have these compact circuits, but bring back the information about the fermionic sign? And this is done by this circuit here. So this circuit is almost identical to the one we saw before for qubits. There are 2 differences. So we have these 2 CNOT staircases and containing also a CZ gate that brings back the information about the fermionic sign. And there is an additional sign factor in the angle, and this takes into account that qubits and fermions obey different algebras. The important thing is that we can have fermionic excitations with just 2 CNOT staircases independent of the excitation run. So we go from 2 to the 2n CNOT staircases to just 2 CNOT staircases. And this is an example of a double fermionic excitation. And this is how the circuit looks like after you decompose this multiply controlled RY gate. So we see that we replace the 16 CNOT staircases by just 2 CNOT staircases and 14 CNOTs in between. So this is a major saving. So before I go to the numerical results of our simulations, I will go through some computational details. In our paper, we looked at 2 different approaches. We looked at the variational and projective quantum eigensolvers. Both of these methods use an ansatz that has a similar form. You have this parameterized unitary acting on your reference state, and the parameterized unitary is a product of these exponentials. In both approaches, the energy is computed as an expectation value, which means that both VQE and PQE can give you upper bounds with respect to the exact energy. Where the two methods differ is on how you compute the optimum parameters for these T guys. In the case of VQE, the optimization is done variationally. So we're looking to find the parameters T that will minimize the energy, and this translates into computing the gradients of the energies with respect to the T amplitudes and setting them equal to 0. In the case of PQE, we use an approach that is similar to traditional coupled cluster theory, and we compute the residuals and set them equal to 0. Now, both VQE and PQE can be used with fixed Ansätze, and what I mean by fixed Ansätze, meaning you have a fixed number of exponentials. So for example, that would include UCCSD, UCCSDT, and so on. But what is more important and economical is to use iteratively constructed Ansätze. So in this case, you have to define a pool of operators, and that pool can contain singles and doubles, generalized singles and doubles, singles, doubles, triples, and so on. And inside that pool, you have your unitaries swimming around. And this bucket here will represent your ansatz. So one way to do this selected approach is to add one operator per macro iteration. And you can see that in this example, once an operator is selected to be added to the ansatz, it is removed from the pool, which means that the pool is allowed to drain. Another possibility would be to, again, add the operators one by one, but in this time, you do not allow the pool to drain. And what that means is that a given operator can be added multiple times to your ansatz, albeit with a different parameter. So in this particular example, the operator U13 was added twice. Another possibility would be, instead of adding one operator per macro iteration, to add a bunch of them. So in the first macro iteration, we add these 3 unitaries. In the second, we add these 2 unitaries, and so on. And again, this can be done by either draining or not the pool. In our work, we considered 2 of these iteratively constructed Ansätze. In the case of VQE, we looked at adapt VQE. And for PQE, we used SPQE, which stands for selected PQE. So for adapt PQE, we used an operator pool of singles and doubles and their generalized extension. And SPQE, we used a full operator pool containing up to n tuple excitations, where n is the number of electrons. In adapt VQE, the selection criterion was based on gradients. So what you do is you compute the gradients of the operators that you have in your pool. You find the operator with the largest gradient, and this operator is added to your ansatz. For SPQE, we use a selection criterion that is based on the residuals. So you compute the residuals for the operator in your pool, then you find the operator that has the largest residual, and you add that operator to your ansatz. In the case of adapt PQE, the operator pool was not allowed to drain, and this is what allows adapt PQE to actually target the exact full CI solution and not UCCSD or UCCGSD. For SPQE, because we use a full operator pool, the pool is allowed to be drained. For adapt VQE, we added operators one by one, while in SPQE, we add multiple operators per macro iteration. And this is the standard way that these approaches have been used in the literature. So now we can move on to the results of our simulations. So the first thing we looked at is, how does the standard fermionic SPQE method contrast with our fermionic SPQE, the CNOT-Efficient one, which we call FEB. And for this test, we looked again at the symmetric dissociation of the H6 linear chain with a minimum basis. So here we have the errors with respect to full CI, and you can see that when we use our novel quantum circuits, we reproduce the energies of the original SPQE exactly. And this is a numerical verification that our circuits are identical, or not identical, they're equivalent to the ones that were used before. However, by using our novel circuits, we were able to tremendously reduce the number of CNOTs. And it is impressive because you see that as you approach the strong correlation regime, which goes from left to right, the reduction in the number of CNOTs is much more impressive. So if we focus at the last point, which is the 2 angstrom geometry, we were able to reduce the number of CNOTs by a factor of 15, which is pretty good. So now that we know that these circuits work really well, the next thing we looked at is which one of the 2 variants is best. Is it the fermionic or the qubit one? So for this, we looked at 2 systems. We have the symmetric dissociation of the linear beryllium hydride and the symmetric dissociation of H6, both using a minimum basis set description. And first, we looked at the errors with respect to full CI. In both cases, you see that in this case, it's like a tie. It's difficult for you to say whether the qubit or the fermionic version is the best. And at first, this might seem surprising because before I said that the qubit methods have a slow convergence towards full CI. But the thing is, in these examples, we have a very tight convergence criterion that allows both of these methods to converge very closely to full CI. So these are errors with respect to full CI in millihartry. Nevertheless, we can gain more insights if we look at the number of parameters that the fermionic and the qubit approach requires. As it turns out, both the fermionic and the qubit method need approximately the same number of singles and doubles, but the qubit approach needs many more of these higher rank clusters, triples, quadruples, and so on. And the reason that the qubit approach requires these higher rank clusters is to bring back the information about the fermionic sign. So in this case, the fermionic method clearly wins. It leads to more compact unsets. Now, what about CNOTs? It is not yet clear, based on the information that I've shown you, whether the fermionic or the qubit method will require less CNOTs. Because the qubit approach requires more operators, but then the fermionic approach has the 2 extra CNOT staircases. Now, as it turns out, in the case of SPQE, the fermionic method will win. So fermionic SPQE requires less CNOTs than the qubit SPQE. And that does make sense because in the case of qubit SPQE, we have more triples, quadruples, and so on. And there is an exponential scaling with the excitation rank in the number of CNOTs. The last thing we looked at is how many residual element evaluations do we have to do for these methods. And because the qubit SPQE has more operators in the ansatz, it typically requires more residual element evaluations. So again, the fermionic approach wins. So based on these numerical results, we can determine that the fermionic SPQE is the way to go. So now that we know that the best variant of SPQE is the fermionic one, we wanted to compare against the best variant of adaptive QE. And as it turns out, in the case of adaptive QE, the qubit approach is the one that leads to less CNOTs. This is because adaptive QE uses an operator pool of singles and doubles. So even if you require more single and double operators to restore the information about the fermionic sign, the number of CNOTs that they bring is much less than those included in the CNOT staircases in the case of fermions. For these numerical tests, we looked at the same systems as before, and we compared the fermionic SPQE with qubit adapt using 2 different operator pools. We have singles and doubles and generalized singles and doubles. What we see immediately from this graph is that if we use adaptive QE with singles and doubles, we're not able to produce results that have chemical accuracy for all of the examined geometries. However, if we replace singles and doubles by generalized singles and doubles, adaptive QE is practically exact across the board. If we see how SPQE performs, we see that it is competitive with adaptive QE with generalized singles and doubles in the weakly and moderately correlated regimes. But as we go towards strong correlation, SPQE somewhat loses in accuracy. But I would still like to emphasize that in this point here, we're still 1 order of magnitude better than what is known as chemical accuracy. So SPQE is still highly accurate. Next, we looked at the number of ansatz parameters that these methods require. And we see that adapt VQE with generalized singles and doubles, which is the most accurate in terms of energies, requires the largest number of parameters. At the other end of the spectrum, we have adapt VQE with singles and doubles, which was the least accurate in terms of energetics, but also requires the smallest number of parameters in the ansatz. And SPQE is somewhat in the middle. Where SPQE clearly loses is when we come into the number of CNOTs, and that does make sense because SPQE utilizes a full operator pool. So we see that there is a somewhat large disparity in terms of CNOTs. But I would like to emphasize that by using these CNOT-efficient circuits, we were able to bridge the gap between SPQE and adapt VQE by a factor of 2. So at least we're going towards the right direction. Where SPQE has a distinct advantage is when we compare the gradient element evaluations in adapt VQE with the residual element evaluations in SPQE. So in this case, SPQE requires 1 to 2 orders of magnitude less element evaluations. And this can be mainly attributed to 2 factors. So in the micro iterations of SPQE, we use the DIIS accelerator, and this allowed SPQE to converge within around 20 micro iterations. And furthermore, for SPQE, we added multiple operators per macro iteration. And this allowed us to converge within 4 to 5 macro iterations. But for adaptive VQE, you have a number of macro iterations, which is equal to the number of operators in your ansatz. So far, we have seen that SPQE is quite competitive with adapt VQE, but where we clearly lose is in the number of CNOTs. So the question that Francesco and I tried to answer in our follow-up paper that was submitted this morning, so fingers crossed, is how to further reduce the CNOT requirements of SPQE. So if we go back to the n-tuple qubit excitations, because they're somewhat simpler, we see that the main source of CNOT gates comes from the decomposition of this multiply controlled RY gate. Now remember that the implementation that we opted for was the same as Jordanov and coworkers, and it requires an exponential number of CNOTs. As it turns out, if you read the literature, there are more efficient implementation of these multiply controlled RY gates. In fact, there exists one that requires a linear number of CNOTs. Nevertheless, it also needs a linear number of ancilla qubits. So that is not necessarily good. Recently, there was another implementation that requires an n-square number of CNOT gates, much better than what we have, but not as good as a linear scaling. And a couple of months ago in the archive, there was submitted a paper that uses a linear number of CNOT gates, no ancilla qubits, but there is a large prefactor of around 30 something. The good thing about these implementations is that there is no approximation. These are exact implementation of the RY gate. But what Francesco and I looked into is it possible for us to have a linear scaling CNOT count with a very small prefactor? And what we did is we looked into approximate implementation of this RY gate. So we know that this quantum circuit will implement a double qubit excitation exactly. So it performs these transformations. First, we looked at a very drastic approximation where the multiply controlled RY gate was replaced by a single qubit RY gate. And the question is, what exponential is represented by this circuit? So if we looked at how the various base states are transformed, it is easy for us to deduce that this quantum circuit represents the product of these 8 exponentials. The first 3 exponentials operate on the n-electron Hilbert space. The next 4 will either attach or remove 2 electrons from your system, and the last one will either attach or remove 4 electrons from your system. Furthermore, these 7 exponentials, depending on whether you have alpha, beta spin orbitals, they may break the SZ symmetry. So you have m sub s values ranging from m sub s to m sub s plus minus 1 and m sub s plus minus 2. So we see that by making approximations in this multiply controlled RY gate, you can reduce the number of CNOTs, but you're also introducing symmetry breaking. So the question is it possible for us to minimize the number of CNOT gates and somehow minimize the loss of accuracy and the symmetry breaking introduced by this approximation? So we examined various such approximate schemes, and we found one that worked best, and this is the recipe. So in the case of single and double excitations, there will be no compromises. They will be treated fully. When you go to triples and quadruples, we will only keep controls over qubits that correspond to occupied spin orbitals. For pentuple and higher excitations, we will remove all controls. So essentially, we are replacing the multiply controlled RY gate by a single qubit RY gate. And by doing that, we have a linear scaling that looks like this. So this is a linear scaling with a small prefactor when compared to the factor of more than 30 from the previous implementation. This new approach was termed AFEB for approximate FEB, and we compared this approximation to its parent approach. And for these preliminary results, we looked at the symmetric dissociation of the H6 linear chain treated with a minimum basis set. And here we have the errors with respect to full CI. We see that this approximation, shown in red, faithfully reproduces the energy of the parent approach, shown in blue. And here we have errors which are in millihartree. So in fact, our approximation reproduces the parent approach with microhartree accuracy. So it is highly accurate. If we look at the number of ansatz parameters, by doing this approximation, you essentially recover the same number of parameters as the parent approach, which is good. And if we look at the CNOT count, we were able to drastically reduce the number of CNOTs. Especially if we focus on the strong correlation regime, we were able to reduce the number of CNOTs by a factor of 4. So now SPQE is competitive with adaptive EQE when it comes to CNOTs as well. And this approximation is also characterized by a very low number of residual element evaluations. So now you may be wondering, well, what about the symmetry breaking that you talked about? We also looked into that. So here we have the expectation value of the particle number and the expectation value of SZ. And you will see that these expectation values lie exactly on top of the corresponding eigenvalues for the ground electronic state of H6. However, expectation values are not a good metric for symmetry breaking because the contaminants that we have can have either lower or higher eigenvalues. So in these plots, we also have the standard deviation, which is computed in this way. And we see that these standard deviations are quite negligible. So this is a good indication that the symmetry breaking is very, very small. The definitive proof comes from these plots. So what we plot here is the contribution to the wave function of the various symmetry subspaces of the Fock space. So on the left, we have the parent method, and there is no symmetry breaking here. So we see that 100% of the wave function has SZ equals 0 and N equals 6, which is good. When we go to our approximation, we see that 99.999% of the wave function has the correct symmetry properties, and there are various symmetry contaminants, but the weight is very, very small. So we're confident that at least for the systems that we have looked into, that this method, the symmetry breaking introduced by this approach is negligible. So to summarize, we constructed CNOT-efficient circuits for fermionic and qubit excitation of arbitrary rank. The savings in terms of CNOTs are more impressive as the excitation rank increases. As the strength of correlation increases, so does the CNOT efficiency of the novel circuits. And if you want to have a linear scaling, we can do that by making some suitable approximations to these RY gates. At this point, I would like to thank the Evangelista group. I would also like to acknowledge the Quantum Chemistry for Quantum Computing Research Collaboration. Thank for the funding and the software we use. So we used Psi4 for the 1 and 2 electron integrals, and we used QForte to perform the numerical simulations. And QForte is a program written by the Evangelista group. Thank you very much for your attention.
All right. Thank you very much, Ilias. That was a great talk. Do we have any questions from the audience? Oh, we have a few. We'll start in the back. Yeah.
Hey, it's good to see you, and I live in Baltimore. I'm just kind of wondering, so all your results look like noiseless. So I'm just wondering, were they found optically, or how were they found to be like that?
Yeah, unfortunately, I could not hear the question. So
Sure.
if
If you
Jacob,
could speak to,
translate.
yeah, if you could speak sort of to, oh no, actually it would be, thank you. Yeah, yeah. So, sorry, I think the question was about the results being noiseless.
Results look like they hadn't.
Yeah.
And I was just wondering. Okay.
So yeah, the results look like they have no noise on them. Could you comment on that?
Yeah. So this is a perfect state simulator. So we don't have any noise. The thing is that by reducing the number of CNOTs, you would also be reducing the noise on an actual hardware. We haven't done any simulations including noise.
So it sounds like you're investigating the systematic error in the final state versus, yes, we're not taking like sampling of the output of a computer. Yeah.
Yeah, and of course, by reducing the number of CNOTs, your circuits become smaller. So this also helps in terms of the decoherence error. It's much like the run on the quantum device will be much shorter. So you're also tackling that aspect of error.
Cool. Yes.
Maybe relay my question. I didn't catch the definition of generalized singles and doubles.
The question is about the definition of generalized singles and doubles.
Yeah, so I can.
If you could just maybe go back to that.
Yeah, let me. Well, I think it will be faster if I go this way. So. Yeah, so in this case, these are the conventional single and double excitations. So you have indices. So this index here for a single will always be an unoccupied spin orbital, and this index here will always be an occupied spin orbital. When you have generalized singles and doubles, you replace these indices by PQ and PQRS, and these indices can run on both occupied and unoccupied spin orbitals.
Going back to some work that Fiona did with the grad student a long time ago, there was a demonstration that it allowed for movement not only out of the occupied orbitals into the unoccupied orbitals, but also movement beyond that. That you really only needed two excitation operators, the two excitation and the excitation operators, and what you apply to the reference to the function. So I wonder, is that the same case for the GSD?
So I want to do my best to relay this excellent question on something I don't know much about, but it sounds like these generalized operations that allow for excitations both ways. There's some previous work in which you only needed to have double excitations.
So there was a
Sure, please.
major discussion around 2004, 2003, those days. That's what Hans was referring to, about whether an exponent of a 1 plus 2 body operator or just 2 body operator can generate the exact state, because the Hamiltonian is a 2 body operator. And we demonstrated in particular that this is actually a possibility, and we showed numerically that you reference full CI within 6 decimal places, for example. So that's what I think you were referring to. Right? The question is how.
But the Nguyen conjecture, right?
That's how it's called sometimes. We don't call it that way. Yeah. Anyway, you know our work on this with Peckham Fan, and Carol Kowalski. So yeah, so I guess the question.
So the question is, yeah. So,
GSD is free.
yeah. So the question, yeah. some people call it, I don't like the term because it's not same as the others really. They are one and two body operators. Generally.
Cool.
Thank you.
Yeah, Ilias, I don't know. It sounds like, yeah, go
I
ahead.
would have to say that one thing with when you use these generalized singles and doubles, at least for quantum computing, because right now we're very limited in the number of qubits that we have. So, you know, we only use minimum basis sets. So if you use UCC GSD, you will be over parameterizing. You will end up with many more operators than full CI. So, you know, you will get the exact result, but for the wrong reason, I would say. Of course, when you use these adaptive ansatz, you never over parameterize. So you're approaching full CI by adding operators either one by one or, you know, a bunch of them.
Great. So it sounds like we're good there. And Nathan Jansen from the audience has a question. Or the audience from online has a question. I can read it to you. He says, "Hi Ilias, great talk. Since it seems that the simplification happens during the trotterization/mapping, I was wondering if these CNOT-efficient circuits can also be used for the phase estimation algorithm."
So for the phase estimation algorithm, you have e to the IH, right? If I remember correctly. But the thing is that these tricks require anti-Hermitian excitations, which are not present in the Hamiltonian. So you could make some kind of approximation, I guess, which is this is similar to QuIC, the quantum imaginary time evolution. So yeah, you could make some approximation to it, but I'm not sure how well it would work. Yeah, I also thought about the quantum phase estimation, but I'm not sure.
I might have one comment on this, which is, as you're sort of pointing out, Ilias, it's sort of the question is how well can this approximate the dynamics when you get rid of these fermionic excitations and replace them with qubit excitations, and because the way you're using them here, it seems like that choice you're still able to do quite well or even better for doing the ansatz, and that's really great. But yeah, I'm also curious if these sorts of approximations, how well they also work for dynamics, and then you would be able to use it for phase estimation.
Well, in any case, I would prefer to use fermionic excitation, so that's why we're also using them. You know, you will have to have two more CNOT staircases. I don't think that's really bad in terms of cost. You know,
And actually, may I ask a question based on that? So you were able to recover some of the fermionic relationships with these just a couple of staircases of CNOTs. So when you say recover, I'm just curious the degree to which you're referring to.
well, they're
is it an
equivalent.
exact recovery, or is it
yeah, it's exact. It's exact.
An exact recovery? Okay.
Yeah.
Well, that's quite nice then. Great. Other final questions?
I have a question. Hi, yes, Peter. So good to see you again. Yeah, come back sometimes in person.
I will. I definitely will.
Okay, nice talking. So I have a question about this trotterization because I know that I'm just looking at it actually now. A couple of years ago, Nick Myhow published a paper about this trotterization, that the results may depend strongly how this is done. You know, TNT dagger do not commute. So, you know, the basic assumptions, right, have to be taken into consideration, right? And he's showing examples in this paper a couple of years ago that the energies can vary quite a bit when you choose different orderings. Is that important for you?
Well, what we're trying to do is because we do this iterative construction of the ansatz, we're somehow I wouldn't say this problem is solved, but I would say this problem is less severe because we're adding operators based on some criteria that tells us that this is the operator that has to go next. There is one paper with something known as DISCO VQE, and what they're trying to do is like a global optimization. I'm not that much familiar with it, so I don't know how well it will perform. But yeah, it would be also good for us to see if there is some way to do this global optimization.
Okay,
Another
cool.
approach is also like the overlap adapt VQE. So in that case, what they do, which of course is not practical. It's most about, exploring the space, I would say. So you already have the full CI wave function for your system. And then what you do is you compute the overlap of, the various operators, and you're adding operators that maximize the overlap with respect to full CI. But again, in this case, it's most about, the mathematics of it rather than solving a problem, because if you already have full CI, then why do you need to run something?
Okay, great. I think for sake of time, we'll stop it there. So let's give Ilias another round of applause. And yeah, we're really happy you came and gave this talk, or came virtually. And as I think your former advisor alluded to, perhaps we can have you back in person sometime. So.
Of course. It was great to see, as I said, familiar places. I saw Kjörer, Professor Hunt, very, very happy.
I think they're
Thank
happy to see you too.
very much for having me. I really, really appreciate the invitation.
All right. Well, thank you very much for coming, as I said, and I